Good afternoon, dear students. Today we will talk about electric dipole. First of all, what is an electric dipole? Electric dipole is an arrangement of two charges plus q and minus q. These are equal in magnitude and opposite in polarity. They are separated by a small distance. By convention, the distance of separation between the two charges is taken as 2a. 2a is the distance of separation between the charges plus q and minus q of an electric dipole, and this separation distance is very small, of the order of angstrom or nanometer or even micrometer in textbook examples. So essentially this distance between the two charges plus q and minus q remains fixed or constant. It does not change with time. So the dipole moment of this electric dipole is a vector quantity and is given by the magnitude of one of the charges, that is q, multiplied by the distance separation, that is 2a. This distance separation also called the length of the dipole, and by convention the direction of this dipole moment is taken from minus q to plus q. So I will take this a also as a vector from minus a to plus a, minus q to plus q. So p gives the dipole moment of this dipole. Now again the unit system for this electric dipole moment can be easily seen from the relation p is equal to q into 2a. Q has units of coulomb and A has units of meter in SI. Therefore, the unit will be coulomb meter for electric dipole moment. Now, let us see what is an electric field due to this electric dipole. What will be the electric field due to this electric dipole? First of all, we will analyze the situation where we will have to determine this electric field on the axial line, on the axis of this dipole, that is along the length of the dipole. So the point of observation or point of calculation will be point P on the axis of this electric dipole. Minus q plus q charges separate by distance 2a, and if O is the center of dipole, the point of observation is x units from the center of the dipole. Therefore, plus q charge will be at a distance of x minus a, and minus q charge will be at a distance of x plus a. We know that the electric field due to a point charge at a point P, if q is charge, then electric field due to this charge q at a point P or distance or x distance from the charge q is given by E is equal to q over 4 pi epsilon naught r square or x square, the distance between the point charge and the electric dipole and the point of observation. So keeping that in mind, we can calculate the electric field due to this plus q charge at point P. Therefore, I can call it as E1 will be equal to q over 4 pi epsilon naught r minus a whole square, where r minus a is the distance of plus q charge from the point of observation, point of calculation, point P. Similarly, the electric field due to minus q charge will be q over 4 pi epsilon naught r plus a whole square, where r plus a is the distance of minus q charge from the point P. So to calculate the net electric field, also we will also see what is the direction. Since for calculating the electric field, we consider a positive test charge at the point of observation. So if it is a positive charge at the point of observation and due to plus q, there will be a repulsive force. So the direction of the electric field E1 will be away from point P. It will be away from point P, and due to minus q, it will be towards minus q. So these directions will be opposite. And also the strength of plus q at P will be larger than the minus q, because P is much closer to plus q, and it is away from much farther from the minus q charge. So net electric field will be the difference of the two. It will be E1 minus E2. So E net will be, I can take q by 4 pi epsilon naught common, and I have 1 over r minus a whole square minus 1 plus r by a whole square. I can then make some simplifications and write as a by cross product. I can write it as r square plus a square plus 2ra. It will be minus r square minus a square plus 2ra divided by r square minus a square whole square. Using the identity a minus b into a plus b is equal to a square minus b square. E net will be given by q over 4 pi epsilon naught r square will get cancelled, a square gets cancelled, and it is we are left with 4ra divided by r square minus a square whole square. Then I can write this expression in terms of the dipole moment, q into 2a divided by 4 pi epsilon naught into, we are left with 2r over r square minus a square whole square. So q into 2 is the dipole moment, therefore E net will be 2r into p over 4 pi epsilon naught r square minus a square whole square. Now, since the vector quantity electric field is a vector quantity, P is also the vector quantity, so the direction in the vector form, it will be 2 into r into vector p. The direction of the electric field will be in the direction of the dipole moment, that is minus q to plus q. So I can write it as 4 pi epsilon naught minus r square a square whole square. This is the vector form of this electric field intensity at point P in terms of the dipole moment P of the dipole. So now it is a special case when the dipole is very small, or the distance or the point of observation P is far away from the dipole, that is r is far greater than a. The point of observation is very far away from the center of the dipole, such that we can neglect r square minus a square can be approximately equal to r square. Then for short dipole, E net axial for short dipole will be 2 rp over r is for 4 pi epsilon naught, so that we can easily see that for a short dipole, one of the r gets cancelled, we are left with 2p over 4 pi epsilon naught r cube. So for an axial point far away from the dipole, the electric field intensity will be given by 2p over 4 pi epsilon naught r cube, and therefore we see that E is inversely proportional to r cube for an axial point for a short dipole. Thank you.